in order, are we all going to just be on our computers? Thank you.
Let's try again.
Infinite series, again, is the meat of BC. Right? It's not easy because it's your first time learning a lot of it, and you have to pay attention, ask questions, do the homework. Okay? So that's my 10 cents there. But in order to study series, it's very helpful if you learn what a sequence is first. Okay? So a sequence is basically just a listing of terms that follows a pattern. Okay. And we can fit functions to sequences. And we almost always use an n, because that means the term number. I think you've already seen that with series. N equals 1 to infinity. A little bit, but we can fit a function to that sequence that defines it. Do you see how this would be matched to this? Like plug 0 in, you get 1 over 1. Plug 1 in, you get 1 over 2. Plug 2 in, you get 1 over 4. Right? So that. Now, the thing about sequences is they're not continuous, right? Because the x values or the n values are integers. They are not real numbers. Okay.
Oh, so there's discontinuity between one and one.
Right, so graphically what you're looking at,
Usually get a bunch of dots.
yeah, it's going to be a bunch of dots. That's all it is. Make that one. So graphically, 0, 1, 1, 1/2, and then that's what that sequence would look like. So we've talked about the word converge, right?
Yeah.
Where does that sequence converge to?
0.
Yeah, it converges to 0.
So why does the n have to be initially? Because wouldn't 2 n to the 1.5 be between 2 n to the 1 and 2 n to the second?
It would, yeah. But the lead into this series is that when we take these terms and add them up, what happens? Right, so if we had a real number definition, we have a continuous function. Anytime you added all those up, they would just diverge. Right, it would just go to infinity.
Sure.
Every time. Okay? Unless you have an alternating, but then it will be 0, basically. So we define these by integers, so we can study the convergence and divergence of different sequences and series. So some of them do converge. It does have some applications in different areas of science that I can't think of right now that I'll have to come up with that were in my brain. You guys know what fractals are?
See that one?
Fractals? Have you seen those? You've never seen a fractal?
No.
I bet
Sounds
you
like a
have.
fake word.
I bet you $10 you have. Fractal.
No, I'm not gonna take
You know,
that.
I
I don't know
don't
science has
remember the
some
words
big
half the time, so.
strategy.
You're still confused?
So here's the deal. I didn't take the bet, so I'm not going to lose.
Oh,
The problem is if you say no and you say yes, then I'm going to lose either way.
that's right.
That's true.
It's a bad strategy on my part, so I'm not going to take that bet.
Well, you break even at that point, maybe. Cubes. I don't know what that means.
Have you seen those before?
No, it looks like someone got high and then made a picture.
Right, it does, doesn't it? Fractals are, one, a form of art, obviously, that are computer-generated images based on series and convergence and divergence. So the different colors basically represent how fast the series that converges. The black is where the series diverges. We can also do, the amazing thing about this is that a lot of shapes in nature are based on fractals and recursion. See how this is a recursive function. It starts with a box, draw a box in the middle third, draw a box in the middle third of each of those, draw a box in the middle third of each of those. Okay. Recursive sequence, recursive functions are also big because, like, how do trees grow? They have the same process, right?
Fibonacci Sequence.
A bunch of times in a row. So, the what?
Fibonacci Sequence.
Oh, yeah. So,
That's recursive.
all that can be represented with series and recursion, and that's what this chapter is all about, really. Like, this is actually a plant that grows in nature. I forget what it's called. It's like a form of, it's like broccoli, cauliflower. Like, it's kind of a combination between the two. Right. So, but there's some really neat stuff that comes out of fractals, like artistically, but also biologically. Like there. Right? It's trees, they just keep iterating the same function over and over. Each tree has its own function that it's defined by because it's a different tree. Just like we are different people. So, just something that's interesting. Again, it's really high-level stuff. You guys are in, when the applications of calculus, BC, and beyond come into play, you're looking at really high-level stuff. So, there it is. Okay, so one of the things that I'll ask you to do is I'll give you a general term. This is called a general term. Like, so if that's the general term that defines each term of the sequence, right? We can say that n has to be, we can define our domain. Can you generate the sequence? I have not made the sequence. This is what defines it.
So now we have to write.
Now write the numbers. Okay, so plug one in, right?
1 minus 1. 1 minus 1 half. 1 minus 1 third. 1 minus 1 fourth. 1 minus 1 third.
Okay. So like, part of the skill is just to be able to write those out to give you an introduction to what a sequence is. Can you see where that might converge to?
1.
Yeah.
Because it's 1 minus 0.
It's 1 minus anything, right? You get really close to 1, but you never hit it.
So with convergence and divergence, unless it can either be 0 or infinity, unless you have 1 plus, or like a plus or minus somewhere. Essentially. Because you're never going to have like a standalone function that converges to 5. It has to be plus something to get there, right? Because it's always going to converge.
You could probably come up with a sequence that converges to 5.
Really?
Yeah, 5 minus 1 over n.
That's what I'm saying. There has to be like a minus, because you're minusing 0 at the infinity point. Or it diverge because it'd be 5 minus infinity, which would be negative infinity.
Probably. I'm going to think that through, but again, we'll study sequences today and Tuesday, but beyond that, it's really series. Like, add these things up, right? Here's a famous one. A sub n. Yeah, that's not very gangster. Welcome to Friday.
I did not understand that.
He said he thought that was a G, and they said it's not very gangster.
That was stupid.
This is called the alternating harmonic sequence.
So it has to be greater than 0, right?
We will really study the harmonic series where we add the terms up. Let's define the domain greater than or equal to 0. Write the terms.
How can it be equal to 0? Why is it greater than or equal to 0?
The domain?
Yeah.
How do you divide by 0?
Yeah.
That's a good question. We're not going to do that because that would be undefined. Make it blind. I'm on fire. So what's the first term?
Maybe one. One.
Next term.
1/2.
Plug 2 in. 1/2.
Negative 1/3. 1/4.
Yeah, you see the pattern now. Montaigne does at least. So we already talked about alternating, so remember, look at the signs. They alternate because we have that -1 to the end. And then all you have 1, 2, 3, 4 on the bottom. This sequence converges to if you look at the graph, it does this. Right? You guys know what a recursive function is? You've learned that in computer science, right? Have you all been in computer science?
No.
2 years ago.
You're in it? Okay, so one of the things that you can study with this is recursion. Okay. This is what the Fibonacci sequence is a recursive sequence. Because the next term is defined by the 2 before it, correct?
Oh, yeah.
Right, so what is it? 1, 1, 2, 3, 5, 8, 13, etc., right? 1 plus 1, 2. 1 plus 2, 3, right? It's recursive because it's defined, the next term is defined by the terms before it. Okay, so. So in a recursive sequence, you always have to have the first term defined. A term, it doesn't matter which one. It's totally up to whoever writes it. And then you also have to have a definition for the next term. And this is an example. And we'll get, the sequences continue to get more difficult, but so what is A? So this is term 1, right? What's term 2? there?
One.
A sub 1, right? Because it's 2 minus 1?
Yeah.
Okay, plus 2 over a sub 1. So now plug your
Trace.
A1 in here.
Plus
One half,
2.
1 and 2.
3 over 2. Right. Could you do A3? A3 would be 1 half a sub 2 plus 2 over a sub 2, right? And you plug 3 halves in there, calculate. See, that's recursive. Keeps on building. Okay. I'm not going to do that.
I feel like these homeworks are going to be really tedious, Mr.
The sequence ones kind of are, yeah. But it's going to get to where you actually have to think really quickly.
Forecast.
Yeah.
Yes, that's it.
We can also calculate limits of sequences. So let me give you a sequence. Calculate limit infinity of the sequence. Please.
-2. Oh, wait, no.
You remember how to solve infinite limits?
Yeah, highest exponent evaluates what you want.
1, right? N squared over n squared is 1. Okay. Here's what's neat about infinite limits and sequences, and it's actually a theorem. If the limit exists, okay, as it does there, then the sequence converges to the same limit.
So at that point, you don't have to do the sequence?
Right. So we don't have to write any terms out for this. We know that this converges to 1.
All right, what's an example where it converges but there is no limit?
If the limit exists, then the sequence converges to that limit.
So then why do we need sequences? If we can just do it with limits.
Why you don't need to write the numbers out? That's the point of that theorem.
Oh.
Right? But you have to know what a sequence is. Like it needs to be in your mind. Here's a good one. This is our last example. So.
Is that 1 and n?
N plus natural log of n. Okay, what do you get when you plug and chug?
Infinity plus natural log of infinity over infinity squared.
Right. So what can we do with that now?
Well, L'Hopital's.
Yeah. L'Hopital's rule.
No.
Okay, so L'Hopital's rule.
1 plus 1 over x over 2.
No.
It's going to be 0.
So what does the sequence converge to?
0.
0, right? Okay. Any questions? That's it for today.
Why do you have the Lahontan algebra? Why can't you just do n-over-n squared? And evaluate.
Because natural log n
It's the same.
adds value. That's the graph of natural log n.
No.
Looks like. So it also adds value to n. So we don't know, we can't really tell what the relationship is between the two.
Okay.
Like n and n squared, we know the relationship.
Yeah.
But if we add that in there, we don't know the relationship and we can't really say for sure. So we have to use some other method. Whoops. That was not key. Well, my daughter was sick yesterday, so I got her, went home, thinking, hey, it's the flu. I'll have sub tomorrow. I wake her up at 5. She says, I don't feel good. No temperature. I'm like, all right, this is fantastic. I'm going to make a sub plan. So I make a sub plan. She pops out of bed at 6:10. I feel great. Let's go to school. And I'm like, crap.
Really get the grade.
Well, guess I'm gonna wing it today because I had to change everything and then change it back, and it's just kind of a pain. That's why I don't have everything ready. Perfect. Anyways, here's your work. Whoops, that's not what I wanted to do.
Oh,
Come here.
well, he doesn't want it.
I see that. Well, you can see it, so you're good. 10.1. Tuesday,
Wednesday?
Wednesday.
I think we're learning more about sequences.
We are,
Wednesday.
yep.
Got it.
Tuesday, we're learning more about sequences.
So neat.
Okay. I would give it a practice, but I'm not a procrastinator, so there you go. Gosh dang it. It's hard. Let's do that. You. Oh, there we go. Deleted.
Hey, figured it out.
Kind of.